So quality control. By the way, I'm working here at CIIRC as a researcher, and I'm last 3 years making research on AI methods in quality management and quality assurance and so on. So first of all, I will speak not about like management point of view for quality of production. I will speak more about technical perspective. And this, what you can see here, and I can't, is the quality control loop, which we are typically using in manufacturing, for example. You can see a production process, which can be, for example, machining or some other process. And it produces some parts that can be, for example, engine heads in automotive or something else. And from time to time, we take a sample from the sample product, the sample of the output of the process, and we put it somewhere into a measurement center and measure some quality characteristic on it. Then we try to detect if the problem is okay or not okay. We can say if it's in control or out of control. And so we, based on this product, the sampled part, we try to estimate something about state of the process over there on the left upper side. If there is a positive detection of a problem, then a diagnostical part can come, and the operator typically is manually doing it using his expert or her expert knowledge. And then they select a control action which tries to put the process back to the in control state. So this is the control loop. And obviously all of those pieces of this control loop, of this chain, are sources of data that are nowadays normally stored, harvested, acquired, and stored in databases. And then they can be used, for example, by the AI methods. We were trying to do it. I will first describe a small example, which is the focusing on this red part on in the lower right corner, the problem detection or out of control state detection, which can be performed by AI methods. Normally, companies perform it using just comparing the quality characteristics to some limits that are typically computed from data. So typical quality control practice infers some reference behavior, some model of the historical data, and then uses it to compare the new parts that are produced to this reference. That's nice. This is an example of a control chart, which is the basic tool very often used. It's first of all, in the first phase of preparing this control chart, the quality staff is simply computing the control limits from the historical data, and then he uses it in the second phase for detecting the potential suspicious state of the process. So it's very simple. Obviously, if you take, for example, automotive, you can have hundreds of such characteristics, such quality characteristics, and then you can have problem because you have to use like hundreds of those quality control charts, and it can be problem. For many reasons, I do not have time to describe them, but we tried some years ago, we tried to apply artificial or machine learning pattern recognition methods and anomaly detection methods for this problem. We tried to do that, and we found that, okay, that's nice. Here on the right side, you can see some data for two quality characteristics, a scatter plot, and you can see, probably you can't see the colors of the data, but it doesn't matter. Here in the center, you can see the in control state data, where there was no problem with the process. And then on the left, right, slightly, you can see some shifted data from a process which was out of control. And the task is to detect those points. If you look at the purple lines, they form the rectangular area. You can see it's the borderline created by the control limits computed by individual control charts. We, however, looked into multidimensional space and tried to create better, more natural model and more natural control area, which is in blue. The red one is another statistics-based multivariate method, which we compared to, and we found that the machine learning can be advantageously used. That's nice, perfect. Another example is here. We tried to, in another, the previous case was with Skoda car, with automotive sector. Another is example of cement production. And here you can see the same control loop. And the problem is that sometimes it's difficult to measure the quality characteristics. And you would like to reduce the measurements and to save some time. And for that reason, it's possible to replace the measurement by prediction of the quality control characteristics from the process data. So, I'm sorry, now. So you can observe the process and detect if something happened with it directly, and you can even predict the quality characteristics. This is the example. We have the plant, we have the cement production. The main product is clinker. And at the end, on the clinker, we can... Yeah. Yeah. I didn't mention it because I don't have so much time, but obviously it would be run in parallel. Yeah, exactly. But I wanted to show that maybe the science fiction goal could be to remove the quality control or post-process quality control. Okay, so we can measure we can perform some chemical analysis of the output, and we can again detect the state of the process. If we replace it, or if we have data from the process itself, it can be temperatures, pressures, and many others, we can try to detect and predict even the quality characteristics without the chemical analysis, which can be very useful. For example, the main task is to use the model for minimization of energy, of fuel or fuel mix, and keep the quality on an acceptable level. So that's another example. There can be, however, problems, and I think it's not just coincidence that, for example, Pavel Burger was speaking about flexibility, and he was not speaking about quality. Because in my opinion, even if on Wikipedia you will find that flexibility, flexible manufacturing systems improves the quality of production, I think that flexible manufacturing systems will be biggest enemy of the quality operators and managers. Because flexible manufacturing systems are changing and are reacting for changes. Here you can see a change in the clinker example, where they changed a part of the system. They changed the cooler, which is on the right lower corner of the picture. And after the change, you can see the error of the model, which is the third subfigure. And you can see how the error of the model increased. And this can happen, and it happens very often, even in the automotive case, in any of the problems. And obviously, your system must react somehow. So we have machine learning. We know that it brings some benefits. We have flexible manufacturing systems. We can use different methods. And the machine learning, its main characteristic is that it brings benefits if you have enough training data of good quality. And this is something what can easily be not satisfied in flexible manufacturing systems. Okay, we perhaps know some different definitions, and we know that it's some system which reacts to some changes of product, of material, of the process itself, and so on. And we can notice, for example, I was reading this article some months ago, that the number of recalls in automotive is increasing. And I know that even in automotive sector, those systems that produce, for example, engine heads are already quite flexible as well. They are creating different parts, different types of motors, different types of engines, and so on. So I was discussing this with my father, and he told me it's clear because the cars are too complex, too digital, and it's terrible. I want just old car. And he actually agreed with some experts. For example, here you can see one important reason is complexity, but also cost pressure, as somebody mentioned today. And what is very important is that the users of the cars want to have some fun and they want somehow customized cars or products. They have more types of cars and so on. And this all shortens the lifetime of the car and the development cycle of the car. We have increased number of types of car, increased number of car body concepts and so on. So this all increases the product variety and shortens the product life cycles. And this is the problem. This can be a problem because those methods of machine learning need to have enough training data, representative enough good quality training data. But if you change the process, very often you can have problem with this. Okay. So what does it mean? Even in the automotive sector, example, the companies do not use the historical data for computing some limits in the control charts. They use just very often just the specification limits or tolerance limits given by construction departments and by designers of the car. And that's inefficient. And they simply they simply do not use the very simple basic tool which has been developed 70, 80 years ago. And how can we force them to use artificial intelligence methods that are even more sensitive to this problem? Okay, even in some researchers noticed that there is problem with this shortening life cycle and variety of products with flexible systems at all. Even in 1991, they published some paper about this, and they found that there is no strong relationship between between flexibility of the systems and quality. But on Wikipedia, you will find that flexible manufacturing systems improve the quality, and from some point of view, it's obviously true. There are different reasons. They analyzed some different projects of FMS, and they found that very often the quality is not mentioned at all for different reasons. For example, the quality was not improved, so they didn't publish it, obviously. And there are some other reasons. 10 years later, with customized production and customizable production, they simply tried to again focus on the quality issue. And you can find some literature reviews. And still, there was still lack of literature on quality management in flexible manufacturing and production systems. And there was also even some PhD thesis regarding this, and again, they agreed. And I think that the main message of my presentation should be that we should focus more on the quality issues, especially in this new reality of flexible systems of Industry 4.0, and we do it, I'm sure. And now, I don't want to scare you too much. So I will try just to mention some potential solutions that could somehow help us. Obviously, you will find some other solutions probably, but I will just mention some of those that I was dealing with. First of all, very often the parts that come from the manufacturing system, from the process, are sampled somehow randomly or periodically. And this is a big potential benefit, or this could be an added value. We could simply sample the parts from the system, from the production process somehow smartly. Maybe we can increase the frequency of sampling if we detect there could be some problem in the process. Or we can even sample the parts according to the potential benefit for the model itself. So we can use something what is called active learning. Another potential solution or something which could help us is transfer learning. Transfer learning and federative learning. We can simply find a process where we have enough data, which is stable for a long time, and we could simply transfer this, the model which is trained on that to some another process where we not have enough data. Just tune it so we can have a pre-trained model and finish the training on the small data set from the process 2. And another very important thing that we feel very crucial in last years, and also when we discuss it with the companies, is the formalization of the structure of their processes. They very often have a lot of data, but they have also some knowledge, which is owned by a human, but they do not have some knowledge readable by computer, some formal representation. And here, for example, ontologies can help us. We can use ontologies in different manners. One manner is, for example, we use it for optimizing the sampling plan somehow, but we can also use it, for example, for the diagnosis. This is an example of ontology in manufacturing, in machining, of engine head. And the diagnosis is that we are looking for the cause of the problem. And if we add some form of reasoning to ontology, then we can get something, for example, like Bayesian network or something else, and we can compute what could be the cause of the problem using this structure. When we speak about explainability, which was also mentioned today, we should also mention interpretation, which is something what the quality operators understand too. They want to know if they get some alarm, they want to know which quality characteristics caused the alarm, which were responsible for that. And this is what we call interpretation, and there are also methods for this, and all of those methods can help. You can notice maybe that the ontology can be created even without training on data. That's why I mention it here as a solution of that problem, because we don't need data, we need just knowledge, which can be easily acquired. And okay, this is about the interpretation. I thank you very much. The main message was not like flexible manufacturing processes cause poor quality. It was like we should focus more on the quality in flexible manufacturing processes. Thank you very much.